Hello, I am Maximo Rulli, and today I will guide you through our paper, Attention Sinks in Diffusion Language Models. In this work, we study how attention sinks emerge in diffusion language models and their differences with autoregressive ones. To begin with, what is an attention sink? Attention sinks have been characterized in the language model literature as a token that receives an excessive amount of attention from all the other tokens. So, if we see at the self-attention formula, slightly abusing the notation, we can denote Qikj as the attention that token I pays to token j. So, an attention sink would be a whole column in which all tokens, that would be the different columns that we have here, pay attention to a single one. That, for example, in autoregressive models, most of the times it's one of the first few tokens, like the beginning of sequence 1. And we can mathematically define this as a token that receives an attention that is bigger than an amount epsilon compared to the average of all the incoming attentions of all other tokens. So basically, what this formula is telling us is that we define an attention sink as a token that has an incoming attention, or let's say the sum across all rows, that is bigger than an amount epsilon compared to the average of all the other tokens. Now, what is a diffusion language model? Diffusion language models are similar to how BERT work in the sense that they start with masked tokens and they have to progressively unmask them. Different from BERT, diffusion language models operate in a stepwise manner, so they have to unmask tokens some amount at the time and not just unmask everything in one step. So while in autoregressive models, we model sequences left to right, and so we have to generate the token that comes on the left to know what comes to the right. In diffusion language models, what we have is that the whole sequence is masked, and each masked token has to predict what original token was at that position. So in practice, the training loss just reduces to a cross entropy of each masked token trying to know which was the original token that was at that position. And here to the bottom right, we can see a GIF of how these models generate text. Most importantly, these models do not have to generate text left to right, and so they use bidirectional attention, which implies that we will not have the stereo-like attention map that we show on the previous slide, but a bidirectional one, as encoder models do. So what we observed is that in diffusion language models, attention sinks emerge, but in contrast with how they show up in autoregressive models, in diffusion language models, they are highly dynamic. So as we can see in the picture on the left, here we are depicting the incoming attention average across the whole model of each token. So we have 160 approximately tokens in the sequence, and we see that the bright lines are the tokens that concentrate most of the attention. And what we see is that the most important token, or at least the most attended one, moves across the noising steps. So from the noising step, let's say 15 to 16, the most attended token jumps from one position to the other. And we can clearly see this on the image to the right, on the GIF to the right, where the most bright line moves from right to left. Note that this is for Lara and this is for Dream, but we will get into the details of each model in the next few slides. What we also see is that attention sinks are highly distributed across the whole model, and they are not just a phenomenon of a few layers or heads, but they actually show up pretty frequently across the whole model. So here in this video, what we basically showcase is that there are a lot of attention sinks across many heads and many layers that this span basically the whole model. So they are not just concentrated, but they are distributed across the architecture, as it has also been seen for autoregressive models. Now we get into the details of each model. So we studied attention sinks on 3 different architectures: DREAM, LADA, and MADA. They are all diffusion language models, but they vary on their architecture and training data. So DREAM was initialized from Quen and then fine-tuned with the diffusion objective that we showed previously, so just the cross-entropy loss. LADA was initialized from scratch, and MADA is a supervised fine-tuning of LADA, but is also multimodal. And here on this picture we depict the differences of attention sinks across these 3 models. So for example, while DREAM sinks start from almost the last position, they then move towards the center of the generation, and well, they begin to stabilize as we are getting to the end of the diffusion steps. LADA, in contrast, doesn't start from the last positions, but it's in sort of the third quartile of the positions, and it has some progressive jumps in the most important sink. Note that in this picture we are just showing the most important sinks for each model, not all the sinks. So DREAM, LADA, and MADA have many sinks at each of the heads. It's not that there's only one, but the most important one in each of these models shows this pattern. And also in MADA, what we see is a behavior that is pretty close to autoregressive models, because the sink token is mainly fixed across all steps, but well, it has some jumps, so it still moves. And then we also see which tokens are the most attended ones, so which tokens are most frequently the sink tokens, and what we see is that they are mostly structural ones. So it's not tokens that are strictly context dependent, but are tokens that frequently arise across many contexts and are kind of universal to generation. Finally, we tested this model's robustness to masking the sinks. So what we just did is mask the most important sink token at each denoising step. Epsilon 0 means that we just mask one sink token, 1 that we mask 3, and 2 that we mask 10. And what we see is that all diffusion language models, even though we are masking these sink tokens, and these tokens receive a lot of attention, are still robust and can faithfully generate text, and well, they do not lose so much performance. While in contrast, in autoregressive models, so for example in Llama, when we do the same experiments, even masking one sink breaks the model capabilities of generating text. This is interesting because this would mean that diffusion language models are more robust to sink masking, and so we can develop new techniques for efficiency and smarter also KV caching or pruning of these sink tokens. So to wrap up, in this presentation we saw that sinks move across the denoising steps, so they are not fixed as in autoregressive models. The sinks are model and data dependent, so they do not have the same behavior for DREAM, LADA, and MADA. They all move, but each model has their own specific characteristics. Also, sink tokens are mainly structural, so they are not mainly important for generation in the sense that they do not contain valuable information, but are mainly structural tokens. And the models are robust to pruning these sinks, which means that one can discard them without having big loss on generation quality. Well, thank you for your attention, and for your time, and I hope you enjoyed this presentation. You can see more on these links or also contact me. Thank you.